All right, we're going to look at the regioselectivity of the bromination and chlorination. Let's see who's picky, who's not picky. Okay, so look at overall. So the same alkane do chlorination and bromination. For chlorination, we got 40% the chlorine from on the primary carbon and 60% from the chlorine from on secondary carbon. All right, 40 60. But in bromination, really picky where he goes. So 97% go in the middle, only 3% on the primary carbon. Okay, so to be able to explain this observation, we have Hammond's postulate. So Professor George Hammond from Iowa State. So he came up the postulate in 1995. So by the way, so he went to Bates College. Somewhere in the East Coast, I think, somewhere. Anyway, went to do his PhD at Harvard, so he's a super smart guy, and yep, got a tenure at Iowa State University. Okay, this is 1995. All right, let's see what he said about it. All right, so he said that the chlorination. So let's do chlorination right here. Just normal mechanism. All right, so propagation. The chlorination passed through an early transition state. What do you mean by early transition state? Well, the early means the transition state looks more like the reactant, right? So the transition state is a species, the highest energy species in the middle between the reactant and the product, right? And if it's early, so the structure or the energy will be closely to the reactant, close to, that's what we call early. If it's late, the energy right here is going to be closer to the energy of the product. All right. So this is early. So this guy look really similar to the reactant. And if you look at the energy of the reactant, the energy difference between reaction at primary carbon, secondary carbon, tertiary carbon are not that different. Let's say they start at the same position, same energy level there. The transition state, the early transition state, which is similar, like have a similar characteristic to the energy of the reactant, we also have close in energy, right? So the activation energy, I'm going to draw the whole thing here. So CH bond about to break, just about to, right? It's just about to. That's why there's a hydrogen right there. There should not be hydrogen there. Anyway, so this is about to break, but it's really, the structure really close to the energy of the reactant. So all this doesn't have much radical character. Right? What is the radical character? Well, they have a big difference in energy. Reactant doesn't have big difference in energy. You see the difference? This guy have our early transition state, so not much radical character, which means that they all have similar activation energy, and they have the similar rate. The rate are not that different. All right, so the energy just look just like close to the reactant. The energy, activation energy are not that different. The rate either occur at primary carbon, secondary carbon, tertiary carbon, not that much different. Okay, this is the reason why chlorination can happen pretty much anywhere. All right, not that selective. Now, compared to bromination, all right, take a look close. I'm gonna go slow. Compared to bromination, all right, just do bromination there, just propagation step there. All right. Hammond said that the bromination is from a late transition state. CH bond almost break now. It's about to become an HBr, right? Almost break, so late transition state, which means that the energy of this transition will look more like the intermediate of the product on the right side, close to the right side, right? If you look at the product, so this is the product or intermediate in this case. The energy difference in tertiary, secondary, primary. We talk about and the hyperconjugation. Tertiary is the most stable, right? Primary is this poopy, right? The energy difference are large. So the transition state that close to here we call late transition state, close to the product or intermediate, we also have large in energy. Right, draw it out. So this guy, so hydrogen almost close to bromine now, about to form bond, and CH bond almost broken. Okay, so they all have a lot more radical character compared to the chlorination. Right, so what do we mean by radical character? The energy difference between primary, secondary, tertiary are big different. Okay, so they have large radical characters. So the activation energy are big different as well. And that's the reason why tertiary go the fastest and primary go really, really slow. Bromine is really selective to where it will form bond. It will do the reaction with, radical reaction with, right? It always go to tertiary because the activation energy is the slowest. Secondary, primary, the big high activation energy, it won't go there. All right. So my point is chlorine fast but not selective. Bromine slow but really, really picky where he's going to form reaction, to do reaction. All right. All right, now how do we explain the mixture of chlorine? So 40% on primary carbon and 60% on secondary carbon. All right. So look at this compound real quick. There are two types of hydrogen. Are you following? There are two types of hydrogen on this molecule. We have the blue, which is 6 total in this molecule, and 2 in the middle, 2 hydrogen. So we have primary carbon and then secondary carbon. So 6:2 or 3:1 ratio basically. In terms of statistics, right? So chlorine have more places to form bond with, more hydrogen to abstract and to form a radical. So 3:1 or 6:2 ratio or 3:1 ratio. But the stability say no, form right here because this is stable. So there's competition between the number of hydrogen it can form bond, number of locations versus the stability. Less location, but this is stable. They have competition, right? And for these two, we found, so we observed that the stability win by just a little. This is almost tie, right? Just win by just a little. 60% go to secondary and 40% goes to the primary. They are in competition. Statistic, number of hydrogen, and the stability, right? And the activation energy are not different, so chlorine doesn't care. I can go anywhere. We have more hydrogen. Oh, go here. So some of them think, oh, let's go to form something stable. Go right there. We end up with 60% versus 40%. Versus bromination, look at the product distribution, 97% here, look at that. And that's only because the activation energy between forming the secondary radical and forming primary radical, the transition state, the secondary radical goes much faster, right? Normally, how many hydrogen are there outside? I don't care. Bromine want to form just, the reaction goes way too slow. Right? The reaction that from a stable alkene, secondary one, is much faster. So bromine going to go the fastest one right here. This is kinetic explanation. Okay. So to summarize what I just said, the product distribution depends on the competition between statistic and the stability factor. Right? The statistic, how many hydrogen, how many location chlorine can form. Stability, where chlorine can form and stable radical. Right? Chlorine doesn't really care. I can go anywhere. So 40 and 60, we end up with stability win a little, but that's not a lot. This is really kind of useless reaction. You got a mixer. But bromination gives you all the way anything is stable because the reaction go fast there, right? Low activation energy. The primary, no matter how many hydrogen are there outside, it doesn't matter. Reaction goes slow. So only 3%. Most of them go to pick the stable radical in the middle. Okay. All right, let's take a look right here. So if look at the structure of this molecule. There are two types of hydrogen as well. 9:1 ratio. Look at a 9:1 ratio. All right. Now, if you do chlorination, chlorine doesn't care. I can form reaction anywhere. So 65% go outside, 35% go inside. Again, statistic compete with the stability. Right? Statistic win. Hydrogen go totally nine. Too many. There are way too many locations you can form radical with. Right? Bromination on the other hand, nope, 100% go to the middle. No matter how many hydrogens are there outside, doesn't matter. Reaction goes slow, it doesn't occur. The fastest reaction is right in the middle. And think about it. This is tertiary. This is primary, right? I'll take a look at the energy diagram. Tertiary is much, much faster than the primary. This is very unstable, right? Chlorine doesn't matter. Activation energy is real close. Okay, so my point is chlorine is fast but not selective. Bromine slow but really, really picky. Okay, all right. I want to do bromination. Where do you think the product will form? Shouldn't be that hard. One hydrogen right there. Doesn't matter how many hydrogen out there. Bromine doesn't care. From the most stable radical. Nope, no hydrogen there. So watch out. So ta-da. That's it. Okay. All right. Let's go to look at the stereochemistry of the halogenation.